All right, transaction scripting at Multisig.
Take one.
Let's actually synchronize the audio and the video. All right, so last time we talked about Bitcoin overview and we looked at transactions. And transactions have inputs and outputs. I'm going to use some different words today to describe the same thing. So outputs express encumbrances. An encumbrance means a limitation on who can spend something. So when you create a Bitcoin transaction output, what you're saying is this output can only be redeemed by X. And that X is an encumbrance. And the encumbrance is expressed in the form of a script. The most common encumbrance, which we'll see in a second, is the one that simply allows a signature from one of the Bitcoin public keys. So it basically means the only person who can redeem this is whoever has this key. Right? That's the basic Alice pays Bob 1 Bitcoin, and the encumbrance is Bob can redeem with Bob's key. All right. So if you have a transaction, you have a series of inputs and a series of outputs. All right. So you'll have input 0, input 1, etc., and output 0, output 1, etc. All right. You should think of each output as a puzzle that takes a key, right? So let's say, for example, this is an output, right? And this output has a specific input key. That unlocks that particular output, right? So,
Hey, Andreas.
yeah.
Can you write echo if you can?
Right.
Otherwise, it's not catching it.
All right, we'll take a photo of it after. All right. So this output is called the encumbrance. Let's think as it goes. Can anybody see that? All right. That output is called an encumbrance. And Bitcoin terminology is called a script. Hang on, let me make sure I get it right. It's called a script pub key. Script pub key. It's called a script pub key, even though in some cases it might not be a public key at all. Right? Simply because in the original transaction language, it was a script that pointed to a public key, saying Bob's key. It's encumbered by Bob's key. The input key, this one, is called the script sig, which means the signature that unlocks the script pub key, right? So when you use an output as part of an input when you're verifying it, the input is providing this thing, the input key in a transaction. And it's referring to a previous output in the blockchain by reference to the transaction and index. So it's saying, from the transaction X from last week, I'm taking the second output. And here's a script sig that unlocks it. So that's how you define an input. And then you say, and I'm sending that to this new output, which is a script pub key. And in order to redeem that, someone has to offer a script sig when they reference it as an input. Right? So if you think about this, to use the same shapes, these are little keys, and these are little encumbrances. Think Tetris, right? So in a transaction, the output is this bit, and then the input refers back to a previous output and provides a little key that opens it. So if you have another transaction below here, and that has another input, and this pen is no longer working.
Oh, that's better.
Right.
That's one.
So if this has an input, what we're looking for is this input. What would fit there? That goes in here. All right. So this input says, I'm going to use this output here, and here's my key. And a client that's verifying this transaction can go and download this TXO, this transaction output, pull up the script pub key, which is the encumbrance, match it to the script sig, which is the key that you provided, and that produces a verified transaction. And then you send it to an output, which again is a different type of encumbrance and locks it to someone else. And so what you're doing each time is you're removing an encumbrance from your previous output and adding an encumbrance to a new output. Right? You're essentially transferring the value by unlocking it from your ownership and relocking it to the new ownership. So far, so good? All right, notice something here. Inputs don't have encumbrances. The script is always in the output. So here, the input's referring to a previous transaction. It says in transaction 27355, input number 1 is what I'm using. And here's my script sig, the key that unlocks it. One of the critical considerations when you're doing transaction scripting is where does the script, the thing that has lots of data in it, go? There's a critical consideration in Bitcoin in that at the moment, the sender pays the fee to create these encumbrances. So the scripts, which are the outputs, the encumbrances, which are bigger in size, much bigger than simply a key, right? The scripts that make up this transaction are paid for by the sender. The recipient puts a much smaller piece of data, which is the script sig, in their transaction. Right? So there's an issue, a very deliberate issue here, and you'll see how that changes when we talk about pay-to-script hash. With pay-to-script hash, the burn is actually reversed, which means that you only put a hash of the script in here, and then the script is provided as a sig here, and that shifts all of that burden, the data of the encumbrance, instead of being in the output of the sender, is in the input of the recipient. Another thing that does is here, we're putting the data-heavy encumbrance in the blockchain early. With pay-to-script hash, and this is very deliberate, the encumbrance is put in the block only when it's redeemed, which means that the actual large amount of data that goes into the transaction is introduced much later in the process when an output is redeemed. So that was a deliberate change that happened, and one of the reasons pay-to-script hash is used is to shift the load of data from being output in transactions that are paid by the sender and put into the blockchain early, put most of the data as input in the redeeming transactions paid by the recipient who got the value, after all, and go into the blockchain later. And that's an important change because it reduces blockchain bloat, right? You don't actually put all the big data in there until you're ready to redeem it. Make sense? All right, so let's look at the most specific example of a script pub key and a script sig that's used to do the basic Alice pays Bob block Bitcoin, right? So, and I'm going to read it off here because otherwise I'm going to write it wrong. And I'm going to read it again. All right. right? So if Alice is creating an output that pays Bob 1 Bitcoin, that output is going to look like this. Up, hash 160, the hash of Bob's key, op equal verified object. So this transaction scripting language is a forth-like, left to right, stack-based language, right? It's similar to a reverse Polish notation calculator or forth programming language. And what we're going to do is look at how this is actually evaluated by creating a stack and then evaluating the script from left to right. Now this thing, anybody want to tell me what this is? This whole thing? It's found in an output. It has a funny name. It's over there. Okay. So no, this is the script Bob key. This is the encumbrance. This says only Bob can redeem this. This is the encumbrance in the output that Bob created. So this is actually found in the transaction output, and it's an encumbrance. It's a script that limits the redemption of this output to a very specific recipient, whoever can produce a signature matching Bob's hash, right? So that's the encumbrance. And so this is called the script Bob key. All right.
So I always hear this described as like fourth-like language, but I don't know his name. Anyone ever heard of fourth? Anyone? Oh yeah. I don't think most people know what it is. So
Right.
What are the distinctions?
So I'll go into an example of stack-based language. We'll execute this script step by step so you can see exactly how it works. First, let's look how this all fits together. So that's an output, right? How does Alice redeem that? Or rather, sorry, how does Bob redeem that? Bob has to create a transaction, which has as an input a reference to this previous output. This is an unspent output. So Bob would create a new transaction where he would refer to this as a previous input, an unspent transaction output, which is now an input, right? What else does Bob need to provide? The script sig, right? He needs to provide this part. So this encumbrance is in the transaction from Alice to Bob. Now Bob, if he wants to spend it, needs to create an input that refers back to it, right? Doesn't include that script. That's already in the blockchain. It's buried as Alice's output. Bob creates a new input that says, go look in the blockchain, find this transaction. I'm going to spend that first output. And so the second thing Bob provides is a script sig. All right. So, quick detour. Let's have some fun with reverse Polish notation. All right. So this is a reverse Polish notation calculator. It's basically a stack-based calculator. And the way this is executed is, so this is 2, 3 plus 1 times 5 plus 7 times. Okay? This is how you would write a calculator expression in a reverse Polish language. And the way it works is you have operands, basically a piece of data, and then you have operators. And the operators do things to the operands. And they get put on a stack. And the stack is a first in, last out stack, right? So it looks like this. The easiest way to write this is to draw the stack, right? And then what you want to do is you start with your execution pointer, which is here. You start from the left and we run to the right, all right? So the first thing we do is we find data. What do we do with data? We put it on the stack. So 2 goes on the stack, is removed from there, right? Execution pointer moves 1 step further. Yep, what do we do with the 3? Put it on the stack. The 2 moves down. 3 goes on top of it. We're now at the plus, right? What does an operator do? It takes values from the stack, pops them, does the calculation, and then puts the result back on the stack. So what this is going to do, plus is a binary operator. It takes 2 values, right? You can have unary operators. Hash 160 is a unary operator, as is op2. But plus is a binary operator. It takes 2 parameters. So it's going to pop 2 and 3 off the stack. It's going to add them together, and it's going to put the result back on the stack. Done with the plus. Move the execution to the next character. Right? What do we do with the data? We put it on the stack. This is beginning to make sense?
Yeah.
I know it's completely bizarre. Alright, so we move over. Okay, we've got 1 and 5 on the stack.
5.
Multiplying. So that pops everything off, and that's 5.
Oh, so the commands. Okay, so you read left to right. Okay.
You always read left to right. We're just going down.
It's like a
Got it. Yep.
Hewlett-Packard
This is
calculator.
really easy to implement in machine code. That's why we use word-like languages, because in machine code you can implement this using a stack and an abstract state machine that encodes the. It's very easy to read the grammar. You don't need a sophisticated parser. It's very easy to make it secure. All right, so put another 5 on the stack. Add them together. Put a 7 on the stack. Multiply them together. End of execution. The final result is on the stack. Everybody got that? Yeah? It's a lot easier to demonstrate with a calculator. Now let's do the same thing over here with this. So what Bob does in order to redeem this is he provides an input key or a script sig. So this is the script pub key. Let's look at the script sig now. The script sig that Bob provides is a signature. I'll call that Bob sig. And a key. I'll call that Bob key. Right? So far, so good. All right. So what the client does in order to verify this transaction is concatenates them. So what you get on the stack, we'll do the same thing. We'll make a little stack here. We'll make our execution line here. And we'll write it all down. This time, much smaller letters so I don't run out of whiteboard space. So that would be Bob sig, Bob key, OP dupe, OP hash, Bob hash. Fine, I'm going to do it on 2 lines because I ran out of space already. Actually, no, I don't know. Right? So essentially what the system is doing is it's saying, in order to verify this transaction, I'm going to take the script sig, I'm going to take the encumbrance that it supposedly unlocks from the previous output. I'm going to put the script sig followed by the script pub key into my stack language. So here we've got script sig, here we've got script pub key. These came from two different transactions. This one came from the output of the previous transaction, and this one came from the input of the transaction that's trying to redeem it, right? See, there are two different transactions. Alice provided script pub key to pay Bob. Bob provides script sig to unlock that. Are we following the concept here? All right. So, who wants to run through this? Yes?
Question, are these 2 elements on the stack or are they 7?
Oh, yes. 1, 2, 3, 4, 5, 6, 7 items on the stack. It's one continuous script. You concatenate it. Now, that means you can put anything you want in a script sig and anything you want in a script pub key as long as it's one of the accepted standard transactions. It's rather limited. As more and more are allowed, the more complex types of transactions you can create using this technology, right? At the moment, each part of it has to be a valid Bitcoin transaction. So we'll see how this works with multisig too. We'll do some more scripts in a second. Any questions so far?
Gavin said on Bitcoin Talk that creating a test suite to test these conditions or test scripts is something that a project that someone should do to test, your capabilities. I don't know
Right.
what test is. I know we're testing it by hand right now, but how does one create a test suite that's going to test it?
That's a great question. I would expect that you would have to force Bitcoin D to try to verify a raw transaction without getting it from the blockchain, so that you can just feed it a series of raw transactions and see how they evaluate it. I don't know how modular Bitcoin D is if you can simply pull out and invoke the function that does the transaction verification and feed it random inputs, in which case you could create a test suite that includes a whole variety of these combinations and then just have it verified, either individually or the whole thing. Probably the whole thing. Yeah. Alright, so who wants to run through this? Yeah? Okay, so Bob Sig goes on the stack, and Bob Key goes above it. I'm just doing both of those steps simultaneously, so we move this, we move this
Duplicate that.
onto the stack, right? Okay. Op dup, duplicate, takes one operand and doubles it on the stack. So what it will do is actually pop Bob Key, and then it will push Bob Key twice. I'm probably going to do this all wrong and have to try it over again. Alright. Okay, so there's all two. Next. Op hash 160. So op hash 160 takes one operand, pops it off, calculates the 160 double hash of that operand, right? So that's a specifically correct information here. So what that does is two functions. First, it takes the input and it passes it through SHA-256, and then it passes the same input through RIPE-MD160. So Bob Key goes away. 160 goes away, and what replaces it, if all goes well, is Bob hash. So if the key that was provided, when hashed twice and passed through right MD160, should produce Bob hash. So at this point you might be thinking, where did Alice get this? Where Alice got this is she had Bob's public key, right? She had Bob's Bitcoin address that starts with a 1, right? That's just a convenient way of encoding a hashed RIPE-MD encoded key. So if you strip off the version and the checksum off that, what you're left with is a 20-byte, 160-bit Bob hash. So this is just a different way of writing the public key. It just doesn't have the number 1 in front and the 4-digit checksum at the end. It's the strip, the denuded hash. So at this point, we've got a Bob hash on the stack. What happens next?
Verifying the re-
It goes on the stack. All right, so Bob hash, this is data. Data just goes on the stack. So now you've got Bob hash. Bob hash. Bob key. I'll find it. Multisig. So far, so good. Op equal verify takes 2 parameters and produces true if those 2 parameters are equal. So what it will do is it will actually not put anything on the stack. If they're not equal, execution of the script would end here, and the transaction would be considered failed. If they are equal, these 2 values get popped. They get compared. If they're equal, nothing goes on the stack. Execution moves on. So this is essentially a conditional stop. Think about it that way. It's if equal, else, breaks, exception, or exit, or break, or whatever you want to do. So there goes that. These get popped off. And now we're down to opchecksig. And opchecksig takes 2 parameters. It takes a public key, and it takes a signature. And it tries to figure out if the signature has been made by the private key that corresponds to this public key. Right? Basic cryptography function. So it pops both of these. And if Bob Sig was produced by the private key that Bob Key is the public key to, this is the public key. This is a signature generated by a private key. If this signature was generated by a private key that is corresponding to this public key, you don't know it. You don't know the private key. All you know is that whether the signature has been generated correctly. Then it puts true on the stack. And at that point, the transaction is verified. That previous output has been correctly unencumbered or redeemed by this input. That check is going to be done not just by the first network node or client that sees this transaction coming in. It's going to run this verification. Even if it doesn't have a complete blockchain, even if it doesn't know any of the previous transactions, somewhere it's going to have a transaction output list. It's going to find this transaction output and it's going to do the verification. Only if it is correct will it relay it out onto the network. Eventually a miner will get it. The miner will do this same check again. Only if it is correct will this transaction be included in the block. Then that goes into the block. Once it's in the block and that block is mined, that transaction has been redeemed. And now its value has been transferred to a new output or encumbrance. That's the whole life cycle. So who checks this? Who runs that script? Every network node that relays the message before relaying it, and the miners that mine, before including that transaction in the newly generated block. In fact, before even including it in their unverified transaction pool node.
Yeah, and the block itself when it gets added to the blockchain as well, right?
They don't include this in the block they're mining until they've
No, I
mined.
mean, once it's mined and then the block is propagated, it would re-verify whether everyone grabs that block.
Everybody who grabs that block, in order to ensure that that block is correct, if they're running a full node client, if they're running just a light node client, what they're going to do is they're going to verify that the block signature, the hash of the block, is higher than the lower than the target difficulty, and that it hashes correctly with the nonce. But they're not going to look below the Merkle tree to look at the transactions. However, if they're keeping a full node, a full index node, then they verify every single transaction in the block before including it into the blockchain. There is a protocol definition within the wiki that explains step by step what the node and the miner do in order to verify transactions. What they have to do before relaying, what they have to do before mining, what they have to do to accept the block.
Quick question.
Yeah.
So does every operand always consume the value of the stack, or does some of it leave the value of the stack?
Depends on the operand. Some consume one value, some produce an output, some don't produce an output, some consume two values on the input, some
Something that you're accessing a value but you're not going to do it in the stack? Like, is it
no,
all
and that's why you need opdupe.
Oh, okay.
Because the whole point of opdupe is that we couldn't leave Bob key on the stack. It would get consumed by the equal verify. So you have to first duplicate it in order to do the hashing.
So any access to the value of the stack is going to consume it.
Yes, yes. The stack can only, you can't look into the stack or do other things. The stack it only has two functions, push and pop, right? So you either push or pop something. And so there are specific stack commands that do things like looping and popping and things like that. Any other questions here?
I don't think it would rewrite the whole stack every time like that. I would assume it would just write to the top of the stack.
You know, it's implemented as a data structure with a linked list. I have no physical mechanism for moving things up on the whiteboard and moving them down, so I rewrite the entire stack every time. This is a very inefficient stack implementation. But yeah, it would just normally just push things down and move them up. So essentially, it really has a pointer. It will add data to the. It's usually a linked list. So it would add data to the linked list and then move the stack top, the head pointer, to the top item of the list. All right, everybody get that? Sure, my shy. Welcome. So this is a standard encumbrance for a standard transaction. A more complex transaction would be a multisig, but first I want to do a simpler one, which is the Coinbase one. So when you're doing a Coinbase generation, so if a miner is generating a new block, transaction 0 within that block is the Coinbase generation transaction, which basically means from nothing to me, because I found this and therefore I deserve a reward, 25 Bitcoin, right? So the from nothing part means there is no previous output. The first transaction in a block has no previous outputs. It simply has a Coinbase number, which is really just a number. And it doesn't have a prior encumbrance. It's unencumbered. The encumbrance is find the damn proof of work for the entire block. So it's encumbered by 10 petahashes of work. But it has no other encumbrance. So the script pub key is actually a lot simpler. And it looks like this. This is essentially the output, the transaction output of the Coinbase generating entry. In here, it would look like this. So let's say this is a block, a transaction in a block. Right? This is what it looks like, right? So this is the first transaction of block, transaction 0, is from Coinbase, from nothing, to the miner's key. And this specific encumbrance, the Coinbase script 5 key, is miner key object sig. So compare this to this. Make sense? It's a much simpler form because in the case of Alice paying something to Bob, Alice is going to introduce this script into the blockchain. She's doing this with 0 effort. Therefore, we want to make sure that what she's introducing is a fully hashable address. So we first have to make sure that when it's unencumbered by Bob, he produces both the pub key and the signature. And those are compared against the key and the signature. It's a more elaborate dance. The miners have already put 10 pentahashes of work to put this in the blockchain in the first place. So effectively what you're doing is you're trusting them not to put a whole load of crap data in here using this object sig. And it's a less elaborate process for verifying. So that's the script pub key. And then the miner would redeem this by putting it as an, using that output. So this is an output, right? Transaction output. Let's say the miner wants to spend his coin by sending it to Coinbase to get dollars and buy new GPUs. So it would then take that, could be in the next block, and do a transaction input that takes that, provides a script sig, and then transfers it somewhere else. Right? So the script sig that the miner produces is miner sig. That's it. And so that gets evaluated as follows. Yeah. So when the network tries to evaluate the next transaction, which is the miner collecting the reward and actually doing something with it, the network is looking simply to put the script sig, which is the miner signature, the miner key, and object sig. And again, how does the stack-based language work? Left to right. The first operand on the list is data, so it gets pushed onto the stack. Do this quickly. So miner sig goes onto the stack. Then miner key goes onto the stack.
What are they signing in this case? What's the signature of?
Random number. Because you don't care about what they're signing.
How do you verify the signature?
It's a bit more elaborate than that, so I'm simplifying. There's actually a correct process for generating the random number that you use as the nonce in a signature, which is part of the kind of best practices for ECDSA. The bug in Android, which happens because the random number wasn't random, and therefore because you're multiplying that by the key, the private key, if the number isn't random and you know what it is, you can then divide the signature by it and you get the key. Ouch.
Right.
So instead, there's a process for ECDSA for doing this in a more sophisticated manner, where you take a random number, you permute it, you go through a process of multiple steps to make sure that that doesn't get reflected in the signature. Right? But it doesn't matter, because in ECDSA, all you can verify that a key has been signed by the equivalent of a public key without knowing what the underlying thing you're signed is. Right?
I guess I'm wondering, like, how is the signature different in every transaction? Because otherwise it just
Yes,
copies from
it must be different in every
So I'm just
transaction.
based on it.
So that's a null, so it's basically a random number. And there's a more elaborate procedure, so it can't be cryptanalyzed. But if you just took a random number and signed it, that's how you create minor sig. So now, we take object sig, it takes two operands, it compares that in fact, this signature and this key have produced the output. Object sig goes away. True, transaction redeemed. Right? Alright. Alright. Let's do a multisig. Who's ready for a multisig? Yeah. Any questions so far?
When the Coinbase is issued, what the issuing of that Coinbase is done by Bitcoin, right?
It's done by actually most mining software. They put it's done by Bitcoin D, but you can pass other parameters to what gets put into the Coinbase itself. So in the Genesis block, the Coinbase itself contains an ASCII message that says the Times of London, 9th November 2013, Chancellor orders bailout of banks. Okay, that's the Coinbase. So it's, they basically use the Coinbase to stick data in there. Miners often use the Coinbase to put various tags, right? Like, for example, some mining pools, as far as I know, use the Coinbase to say how much the previous block, how it got allocated, or the pool work, or things like that. They also put version information in there. During the consensus election for picking which pay-to-script hash solution to use, Gavin's pay-to-script hash, which is BIP 16, or Luke Jr.'s pay-to-script hash, which was BIP 17, they asked the miners to say, if you start putting in your Coinbase the string P2SH, we're going to do Gavin's. If you put CHV, we'll do Luke's. You have 3 months. Start mining. And some of them put both, we'll support both. And then they did a calculation of all of the blocks. How many had P2SH? How many had C2B? There you go. You have an election. And P2SH won, and BIP 17 is deprecated. So it's actually used to communicate information back from the miners, but it's not used anywhere else in the blockchain protocol. It's just basically data. Yeah? Yes?
Last time we had a meetup, there was a question as to whether you could put in less than 25 or something like that.
Less than?
Like 25 coins. And whether you
Oh.
rejected it or not, did you ever figure out the answer to that?
Yeah, that's a good question. I don't think we did figure out the answer. As far as I remember, we discussed it, and someone said that there are transactions with less than the reward, and they are processed correctly. So the validation protocol for validating a block is the reward less than or equal to, not is the reward equal, but less than or equal to. So you can't put less. All right, so everybody clear? Any questions? Let's do one multisig. All right, I'm going to put a couple of more up just as examples. This is so this is a transaction output that has no encumbrance. So if as your script pub key you put empty, you put nothing, anyone can redeem that. And in order to redeem that, they need to produce a script sig that contains true. What OP true does is it puts true on the stack. Simple as that. Right? Make sense? And so if you put these two together, what you get is a stack that says OP true, and then nothing. And that puts true on the stack. That's a valid transaction. That's basically a null encumbrance. It means anyone can spend this input, this output. It's unencumbered. Why would you do that? Donation to the one way of doing it. Really no practical use for that. Here's a different one. You can't, this is not a standard transaction, by the way. At the moment, you can't actually run this on the network. It will not be relayed.
None of these you can run on testnet, right?
If it runs on testnet, it runs on mainnet. That's the point of testnet is to make sure that it runs on mainnet. So they should be entirely equivalent in terms of strict verification. It's the same software, different blockchain. But it should be the same validation. So this is an encumbrance that requests an answer. Which answer? The one that when you hash it with op hash 256 produces this hash, which then goes through OP equal, and if the hash and the... So the way you would evaluate this, again, go on our stack, it would be concatenated 42 op hash 256 a long hexadecimal number. Yep. We start here. This goes on the stack. OP hash 256 creates a 256 hash. It's a SHA 256 of this. And puts it back on the stack. Then that number gets put on the stack too. And then, are they equal? True, right? So what this is basically what this says is, this output is encumbered by anyone who can find a value when hashed with SHA-256 produces this digital signature. What is it? Nobody knows. You can't tell, you can't reverse it, right? It could be anything. In this case, it's the answer to life, the universe, and everything, 42. But it could be something else. Essentially what this is a puzzle, right? So you're saying this is the puzzle, whoever finds the magic treasure answer can redeem the solution to this puzzle. Another way you can use this is to do a lottery. So for example, you can have a lottery that takes a specific, where you essentially roll the dice, you draw the lottery before you run it. Then you put the result on the blockchain and says, whoever finds the ticket whose hash is this, which is what we just drew as the lottery, you don't know what that ticket is, wins the pot. Now everybody send money in, right? And choose your ticket numbers. And whoever finds the right ticket number can then go back. Then you can announce it and say, that was the ticket number. And everybody can go back in the blockchain and confirm that hash was there, and the person who used it did in fact redeem it. Make sense? Yeah. Satoshi did, yeah, no. It does not do something like that. It used another trick to put information into the blockchain like that. It did use a drawing the number before so that you can verify that it was the correct one or something like that. I'm not exactly sure. That would be a great study, the transactions that go into Satoshi dice and what DOS transaction is and how that works. All right, got a few more for you. This is the encumbrance. I type better than I write. So that's the traditional multisig transaction. It's the number of keys required, the number of keys provided, and the 3 keys. Now, where does this go? It goes in the output. It's an encumbrance, right? And then what you produce in response to redeem this is a script sig that I'm going to find in just a second. Learning as I'm doing, guys. Learning as I'm doing. So I believe the solution to this is key 1, key 3. It's as simple as that. So we provide 2 keys. Well, actually, these are, sorry. Key 1 sig, key 3 sig. It could be 2 and 3, or 1 and 3, or 1 and 2. Doesn't matter. Any 2 out of the 3. So you essentially provide 2 signatures in order to unencumber this output. And the way it's processed then is you put this followed by that on the stack, and check multisig verify actually takes 1, 2, 3, 4, 5, 6 operands off the stack and pops in a true if 2 out of the 3 are valid signatures of that encumbrance. Okay. Anybody tried this multisig?
I've tried it, but
How did it work? It did not.
I actually haven't taken a function, but there's a guys are doing hacks?
Brian is doing it on Saturday.
Okay, sweet. We're gonna. So the whole purpose of doing a hackathon, it's a 5-hour code bash on the every second Sunday after we do this, is to then try and figure out exactly how it works by writing code against it and figuring out where we got it wrong the first time and we're coming back and doing it again. So if you think this is infallible information, see to the beginning of the video where I said it's all wrong.
The part that's a little tricky is where you put in the script pub key there. It's expecting a hexadecimal hash, I believe, of that, or a serialized version of that text. If you
Of
plug
this.
That text, yeah, if you plug that text into create raw transaction, or some
Yes.
raw transaction will work.
Right. Oh, okay. So you serialize this first.
Yeah, that's what I can figure out. Like, how do you actually serialize?
So let's talk about pay-to-script hash,
Yeah.
which is the next topic, and I'm going to wrap up with that in about 10 minutes. So we talked about before the fact that the transaction output contains the actual script, which is the encumbrance, right? And a transaction input contains the key that unlocks that encumbrance. Now what that does is it puts the burden on the sender to create the encumbrance, which usually has more data, and to pay the fee to have that put into the blockchain. So one of the motivations behind pay-to-script hash is to flip that burden. So instead, what you put in the encumbrance is simply a signature of the script, and the person redeeming provides the key and the script in their input, and they pay the fee for it because it's their transaction. So the recipient who gets the value of the transaction pays the fee to incorporate all of that data into the block. So pay-to-script hash is basically a magic Bitcoin address that's not an address. Instead, it's a script. And so the way it works is like this. A traditional Bitcoin address let's say that's a Bitcoin address, right? There's actually 3 parts to this address. First one is the prefix, right? Second part is a 20-byte address. And then the third part is a 4-byte checksum. So a Bitcoin address contains within it a 20-byte hash, the Bitcoin network code, which is 0. When you pass 0 at the beginning of the string and hash it through this algorithm, it pops out as a 1.
When that's created, I mean, if I'm going to sign this transaction and to validate that, I've received these funds, how do I know what's sitting in that transaction?
We'll get to that in a second. Right. So this is not yet a pay-to-script hash. This is a standard Bitcoin address. And in a standard Bitcoin address, what you're looking at really is a base 58 check encoding, as it's called, right? Are you familiar with this base 58? So this is a base 58. 58 check. That's what this is called. What that means is base 58 means we're using 58 characters to encode this this number, this binary number. Yeah. So instead of hexadecimal, decimal, octal, this is 58 decimal, base 58. Why 58? Because they've taken out O, 0, 1, lowercase l, uppercase l, because those are often confused for each other visually. So by removing those, it's harder to mistype this when you're typing it in by thinking that an O was a 0 or an L was a 1 or vice versa. We took out all the ambiguous characters, left 58 characters, uppercase, lowercase numbers. Yeah? 26 plus 26 plus 10 minus the ambiguous ones, 58. And with 58 characters, what you're encoding here is the hash. Remember, in the transaction that Alice created, she doesn't put the key of Bob. She puts Bob hash in the encumbrance. She puts the hash of Bob. Where does she find that? It's right in the address. The address is just the hash with a checksum and a number that tells you which network this is on, main network, test network, etc. Right? Addresses on the test network have a different opcode in the beginning, and so they start with a lowercase m. Addresses in Litecoin have a different opcode in the beginning, so they start with an L. If it's TerraCoin, it starts with a T. If it's Dogcoin, I have no idea. But if it's Namecoin, it starts with an N. So in any case, by controlling this opcode, you generate addresses with different prefixes. The prefix 1 is the main Bitcoin network, right? Then it includes a 20-byte hash of the public key. That's your SHA-256 followed by RIPE MD160. Then it has a 4-byte checksum. And the checksum ensures that if you mistype this thing, it won't be a valid address. So a valid Bitcoin address contains the checksum. All right? So far, so good? So what this is simply a public key wrapped in some fun, fancy stuff to make it more robust for the software that's handling these things. But really, the thing you care about is the 20-byte hash. Right? That's saying encumber this to this output. So P2SH, P2SH. Instead of a Bitcoin address, it's something that looks like a Bitcoin address. So you can use it in a wallet transaction the same way. You encumber towards this address. But instead what it is opcode 3, the hash of the script pub key and a checksum. So for example, you could take op dupe, op hash 160, bob hash, op check sig, op verify. Op equal verify op check sig. You could take the standard pay bob, right? Hash that entire thing, stick it in there, and you could create a new address, which is actually a P2SH hash address, which has the same exact effect as this. Am I making sense?
But when it shows that the blockchain input says not started transaction.
Yes. I don't know.
It says strange transaction. Yeah, that's
Strange.
what we saw the last time. Strange transaction.
Very nice. Well, that doesn't matter. Compliance understands what it is. So, essentially what we're talking about here is that instead of saying pay this public key, you're saying pay whoever can produce a full script and the necessary script sig, and the script has to hash to this. You don't put the script in the output. You say the script will be provided later, and this is its fingerprint. So whoever provides both the script and the key that unlocks it, and you push the script from being in your output to being in the redeemer's input, because they now have to provide script sig, the entire script, and that redeems it. Yes?
So this answers another question I have, which is our scripts that were used when validating transactions with a return value of true or false. This would be the exception. The hash itself
So this gets evaluated very differently. So let's see how this gets evaluated. This is somewhat more complicated. So let's take the same one. We're going to do opt up, op hash 160, op hash. I'm sure beautiful Apple design doesn't drag the laptop onto the floor when you do that. Alright, so this is a standard encumbrance, right? This is a standard script pub key that's used to say pay Bob. Everybody got that? We talked about this before. So instead of putting this in the transaction, what you do is you put this through a hash. And you produce a signature for it, right? You're saying, this is the script that I want redeemed. This is the encumbrance that we want to put up. Instead of putting this in the transaction output, you do it on hash 160 away. Yeah? You then take this and you add to the front of it the opcode 3 and then the checksum, and you create a Bitcoin address. Only this isn't an address that corresponds to the public key. This is an address that corresponds to a full script. And in your wallet, you can simply say, hey, this code, 3ABCD, blah, 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 I'm sending 1 Bitcoin to 3ABCDFG. The network doesn't know what's behind this. You haven't yet produced the script. The script is hidden. You've only shown a fingerprint of it. To redeem this transaction, the redeemer needs to produce this. Based on our previous discussion, Bob would produce Bob Sig, Bob Key, Bob 2, so Bob now must produce a signature, a key, the actual script that this corresponds to, and in order to redeem this, the verification is going to evaluate that script, figure out what its hash is. Is its hash this? If it is, this is the script that it was encumbered against. Now it's going to put it back on the stack, and it's going to evaluate it using the same rules as before. So all you've done is essentially, instead of providing the full script up front, you say, here's a fingerprint. When this is redeemed, the script will be given to you then. You first check that it matches the fingerprint. If it does, then you evaluate the script as if it was the transaction encumbrance. Right? So the recipient who's redeeming this provides the script sig and the script, not just the script sig, not just the key, but the encumbrance too. And the network checks that that encumbrance is in fact the one that had the signature put into the output. Right? So you're not paying to an address, you're paying to the hash of a script to be provided later by whoever wants to redeem this. Make sense? So in a multisig case, again, what would that be? The way to create a multisig that appears as a P2SH transaction is to key 1, key 2, key 3, take that, put it in, you create an address, right? And then you embed that in the transaction as all hash 160, the script address of equal. Right? So you've taken the multisig transaction, you've produced a fingerprint, you've stuck that fingerprint between an alt hash and an alt equal. And what that says is, I'm going to get something here, a script. I'm going to hash that script. When I hash that script, I'm then going to compare that hash to this hash. And if they're equal, then that's the script you use. So let's run the stack. Again, to visualize this, the stack. Right. So what's the script sig that solves this? The script sig that solves this. So the script sig that solves this is script sig, right? And what is that? Key 1 hash, sorry, K1 sig, K3 sig, let's say that 1 and 3 signed, right? So you provide the 2 signatures. Then what do you have to provide? The entire script, which isn't in the blockchain, it's this one. So 2, K1, K2, K3, 3, ops. Multisig, verify. Then in the verification, the encumbrance is added to the end of this. All hash 160. The hash is getting longer to make this a 2-line. 3A, B, C, D. 1, 2, 3. All. This is the entire thing that gets validated. So script sig. Script. Good. Script called key, which is actually a P2SH script called key. So what the network is doing in this verification is it's taking the thing that was in the blockchain, which is the script called key, this thing that you put in the blockchain, the encumbrance. All hash 160, the hash of the script, all equal. The script that you just provided as part of the script sig, plus the signature that you just provided in order to redeem that output. and it runs it all in one continuous stack. And if you unravel this, all it does is it says, hash this whole thing with OP hash. Compare it to this. If it's equal, then you run it. But the way you run it is the same way you run the transaction, which is just this and this together. Yeah?
But OP equal just return the same statement.
What OP equal does is it returns all of this back into the stack to be verified.
If they're equal. If they're equal.
It's actually a recursive verification. So you first verify that the script itself hashes to the correct value. What I mean by that is the first verification that happens is this one. And what that does is it hashes this, checks that it's equal, and then if it's correct, then it takes the second verification, which is this and this, and runs it through the stack again.
So it's not like a normal stack.
It's not a normal execution, it's two executions. Yeah. Okay, this is confusing, right?
So what's the actual purpose of the P2SH? Like what's the end goal?
The end goal is twofold. The first goal is in order to be able to provide very complex scripts, but enable clients that already understand addresses to have a very simple way to say, pay this script. And rather than putting the entire complex script in with a client, what you do is simply put in a representation. So let me give you an example. You're trying to buy a car using escrow. Instead of you trying, or your clients needing to be escrow aware, when you go to the car service, it says, in order to pay this securely, instead of paying Bob, pay this 3 address. It's a script which includes the escrow key in it. It's a multisig escrow key. So you just say on your client, snap a QR, and you say send 1,000 Bitcoin. That's a lot of car.
That's a lot of car.
Send 50 Bitcoin for the new Tesla. Send 50 Bitcoin to this 3 address. You don't know what's in it, but it was given to you by the escrow service. Right? Now, when that goes into the blockchain, it can only be redeemed if someone produces the script that was behind that 3 address. And so that would be the escrow plus your signature that you got the car, right?
So is P2SH stuff like also used for contracts, or is that
P2SH is simply a way of hiding a script inside an address.
So yes or no?
Yes, it's used in contracts, yes. It's used anywhere scripts can be used. It's just a different way of expressing a script. Instead of putting the script as the encumbrance in the output and burdening that on the sender of the transaction, both in terms of their clients knowing how to create such a script, and in terms of the fees they have to pay to put that in the blockchain, even though it hasn't been redeemed yet. You shift that balance. You just put the signature in. The client already knows how to do it because it just looks like an address. And all of the burden goes to the recipient of the value, who has to provide a bigger block of data, which goes as an input in a transaction, not an output, right? And only on the point of redemption whenever that happens. So stuff doesn't stay in the blockchain. It doesn't go into the UTXO, the unspent transaction output memory pool, which is a very resource-constrained thing, because you have all of the unspent transactions from the entire blockchain in there. It consumes a lot of memory. This isn't an output. The output is just a signature. This is all an input, and we don't keep inputs around. We just validate them once. So now it's not polluting the UTXO set at all. The client doesn't need to know the complexity of the script, and it's only used at redemption. And then immediately once it's baked into a block, everyone forgets about it. So that means that these scripts spend far less time floating around in the system. If you did a big multi-sig script and you put it as an output, every client in the world has to keep it in memory just in case someone spends it. And all of that data, and the sender paid for it. And it's there until whenever it's redeemed. So if it's a trust fund that comes true when that person becomes 18, it's going to sit in the blockchain for 17 and a half years, right? You see what I mean? Whereas if you shift that burden to the inputs, The script itself, which is the long part, will only appear once on that person's 18th birthday. It will not be stored ever. It will just go straight into the blockchain. It won't go into the UTXO. It won't be held forever. So this is all a way to simplify the implementation of scripts because all clients can do an address. And only the miners need to understand how to validate if that transaction is a real script. So it limits the number of code, the amount of code that needs to be changed. And it shifts the burden of where the data goes in, when the data goes in, and who pays for the data to go in. So if you read BIP 16, the first chapter is the rationale of why we did this. Make sense? Yes?
P2SH is fully supported by the network now.
P2SH is fully supported as of 1st of January 2012 and was implemented by the miners and relayed recently, I think November. October or November, you started seeing 3 addresses. I think, I'm not sure entirely. Others can tell me. Yes?
When you're doing a 2 of 3,
Yeah.
I guess this will have to be run more than once because you have 2 people who will be essentially presenting their script to verify. You need 2 out of 3 signatures.
No, you have to produce both of the signatures upon redemption in this output. Yeah, it's not in 2 separate transactions, is it?
It can be, yes.
It can be in 2 separate transactions? All right. How does that done?
I don't know how it functions, but what's the Brian? What's the your friend had the wallet site?
Oh, video.
Big Go. Yeah, yeah. They do different transactions.
They do the 2 signatures in 2 different transactions?
It was on the site.
Right, two.
So in a check multisig,
Yeah.
here we're unencumbering, the script sig contains both of the transactions need to unlock it.
Yeah.
And you actually produce this in 2 different inputs in 2 different script sigs.
It is EDO, it's send data objects. I'm not sure how that one functions.
So, yeah, sorry, so, but basically, I mean, he uses standard multisig transactions. So to send out of the multisig address, what he does is you provide, he actually holds one of the addresses. He holds a encrypted copy of the address, which you have to client-side decrypt to send the money along. And then you hold a third sort of backup in case he goes totally out of business. Then you can create a raw transaction with the 2 that you have. Does that make sense?
So you have 2 out of the 3 already.
You have, yeah. You
And
have
the
2 out of
purpose
3.
is not escrow, it's backup.
Right. Yeah.
So that if he disappears,
Yeah.
You can still
so
get
it takes either your 2 or yours and his
Yeah.
in order to forward it on.
Yours
Yes,
is
yes.
But is that encoded in a single transaction?
it's encoded in a single
It's
transaction.
unlocked as a single transaction. I don't know that you can produce
Yeah.
this in 2 different
It could
transactions.
be a layer that you wrote on top of it.
Yeah.
So if you, what you can kind of do with 2 things is you can sign it separately. Like you can have 2 different signings, but then you have 2 different people sign it at different times, and then send it, broadcast it. It also has to be broadcasted. Right?
It only has to be, broadcast
Yeah, it has
as
to be
one
broadcast.
transaction. How you do the dance. Jeremiah, do you use multisig in local bitcoins?
Okay.
Not yet. Don't base it on this. This is probably wrong. This is kind of the high level. The implementation details are a bit more complicated. All right. That's it. That's transaction scripting and multisig. Thank you.
Thank you.